So good afternoon, everyone. We'd like to welcome you to an interesting panel with four stalwarts of the semiconductor industry. So let me start with the introductions, and then we'll delve into question and answers. So first, we have Anand Chandrasekhar. He's the founder and CEO of IRA Technologies, a company that is focused on radically reimagining wireless communications using AI and machine learning. Chandrasekhar is a seasoned global technology and management executive with a track record for delivering results. He has expertise in global markets. As SVP at Intel, he held a lot of roles, including head of Intel's mobile business, server, and workstation business worldwide sales organization. He was also president of Qualcomm Data Center Technologies and vice chairman of Huaxtong Semiconductor. He is known for his pioneering efforts on the Intel Centrino and Atom processors. Next, we have Raghib next to me. Raghib was a technical expertise coupled with astute entrepreneurial skills make for a classic Silicon Valley success story. He's known for founding Cavium. Many of you have used that chip, taking it public in 2007. He led the company as chief technology officer from inception and catapulted to its status as a leader in the security and multi-core processor space, competing with Intel and Broadcom. Later, as COO, he guided product strategy and business operations and was responsible for the company's strategic direction and an annual run rate of $1 billion. And it was eventually acquired by Marvell, where he is currently the president of products and technologies. Welcome, Raghib. Next, we have Ziad Asgar next to Anand. Ziad is our local. So we have imported few, and then we have a local. So Ziad Asgar is a SVP of Product Management and Head of AI at Qualcomm Technologies. He leads Qualcomm One Technology Roadmap for application processors across all business units. Ziad has driven the AI strategy and roadmap in the company to solidify its leadership in on-device AI to meet the growing demands of the Gen AI revolution. He also drives the custom CPU, camera, graphics, audio, video, and security technologies to build the best technology available. And finally, last but not least, we have Samir. Samir is currently the CEO of MEPS. He spent 18 years at TI, where he was VP and BU manager for processors and responsible for the processors and high-performance MCU business. He reestablished TI as a mainstream processors, MPU, and MCU supplier for high-growth automotive and industrial sectors. He also established the company's footprint in embedded AI, software-defined vehicles, and electrification. So we have TI, Qualcomm, IRA/Intel/Qualcomm, and Cavium/Marvell in presence today. So really honored to be in your company. So let me start with the first question. Semiconductor is at the lowest stack of the equation when you talk about AI revolution coming in, but core building block. Is it safe to say that AI reinvigorated the importance of semiconductor and revisiting how we do things? And each of you can chime in on that, what each of you are doing in your respective companies to drive that strategy. Starting with Raghib.
Okay, so you presented in very eloquent ways, lowest level, but just I wanted to rephrase it. It's the foundation of the whole AI. And AI did not enable it. Actually, this enabled, semiconductor enabled AI. So whatever the buzz you guys are listening about AI about, it's all about software. No, it's all about semiconductor. And that is proven by 2 days ago, NVIDIA, like Arab News, you must have seen their quarter result. And that shows you how important is semiconductor to make this possible, because the reason these concept has been around forever. I mean, like 20 years ago, some of those papers were written, but it was not possible to achieve the level of performance needed to make it a reality until the semiconductor advancement happened. So semiconductor, first of all, is critical. Secondly, there are two, it's a solution. When you talk about the performance, it's not about the chip anymore, it's about the overall system solution. So the performance of the AI is dependent on the compute as well as the connectivity, because these models are so big, and how good of a kind of cluster can you build, and data access can you provide, and that is that determines the overall performance. So Marvell actually is leading in, first of all, in connectivity for all these AI networks require optical interconnect or accelerated copper interconnect. So we are actually market leader in optical interconnect and so on. In addition to that, we partner with the hyperscalers to do custom solution because a lot of them do not want to use GPUs and they want to do their custom, and we are a leading partner for that. So yeah, so we are heavily participating in this thing, and in fact, that's the fastest growing segment for us.
Thank you. Maybe Samir, you want to add your perspective?
Yeah, I mean, difficult to follow Rakib on that. I think he covered the points very well, right? So look, I think to Rakib's point, right, AI is starting to become mainstream because you finally have semiconductors which can start doing that. What I'll add to what Rakib said was, we're just in the beginning. So it is definitely given a boost to the creativity, the creative juices to say, what else can we do? Because a linear progression in processing isn't going to converge to a good answer. So there is need for innovation, there is need for new solutions to come out which solve the AI problem differently. And even the AI problem is going to get more distributed, more different. So I think we are in the very, very beginning of a 30, 40-year journey here. And for a change, I think it'll be led by semiconductor capability, because honestly, that's where the limiting factor is. You can see the applications and the things people want to do with AI, there is no end to it. But if you're not able to keep up the pace of innovation on the semiconductor side, the answers won't be pretty because it'll be too expensive and too power hungry. So I think there's work to be done.
Maybe I'll add a couple of points, right? I do agree with the points earlier. Hardware is, of course, critical, right? I mean, AI, to make AI work, is the advancements that we've made in semiconductor technology, in architectures, in just how we basically do the number crunching that's making this possible. But it is the full shebang, right? You got to have the best-in-class compilers. You got to have the best-in-class ML ops. You got to have the best-in-class software that goes along with that. And each one of those levels offers an extensive opportunity for startups and companies to really innovate, to differentiate. And we see that happening quite often. But I think the real promise is something that I think Samir just said, which is semiconductors will also make it possible that this technology that you could think of as just being captive in the cloud can now get to everybody. And that's one of the things that I've been driving for the last 5 years at Qualcomm, which is how do we take this technology and be able to bring it to the devices that fit in the palm of your hands, right? That's really the promise. That's when you democratize this capability. That's when people are actually able to leverage it. And that requires all of those layers of innovation to really come together for you to be able to make that happen. But I think that's when, it's just like web browser. When web browser was relegated to the PC, you had hundreds of millions of people using it. Once you brought it to the smartphone, basically you had billions of people using it. We want to do exactly that with AI and basically bring all those benefits along with the societal benefits to all those people, essentially.
Just a couple of comments to add to that, right? I certainly agree that semiconductors is the foundational building block, and AI wouldn't be where it is today if the semiconductor capability wasn't where it is today, right? The points I want to add are two things, right? AI is still in its very, 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 very early stages of inception, right? That feels a little funny to say that because it's going from, in the words of Scott Galloway and in a recent podcast, it's gone from being an amoeba to a T-Rex in half a nanosecond, right? Or something like that, right? His point was it's going fast. It is going fast, but it's still in its very early stage. So why is that relevant? It's relevant because the workloads are changing very rapidly, right? Anytime your workload changes that rapidly, the underlying silicon takes a while to catch up. I think Samir made the eloquent point this morning that this may be the first time that the applications are ahead of the silicon, right? So silicon has to catch up, right? So again, the foundation has to get invested in for it to catch up. The second point I would make is the energy efficiency of the processors that are being used to do AI today, nowhere close to where they need to be, right? And we can all wind the clock back to say mid-90s, when single-threaded performance on processors was the way you delivered performance, right? And it got to a point where the thermal density on top of a chip got to be the temperature on the sun, And so the technologies available to cool these chips, right, weren't available. So you'd have to invent new things. Clearly not possible. So multi-core processors started to emerge. Intel, AMD, everybody, ARM started to do it. And I think that was basically the right-hand turn. Instead of chasing single-threaded performance, you're chasing multi-core performance, right? And everybody is doing that now. Something moral equivalent of that has to happen on the AI side in order to be able to get the performance per watt to a level where it's tolerable. So I think that's room for innovation, has to happen in semiconductors, won't happen in software.
Yes, I'll double click on both the points you raised about power and then the architecture about edge and the cloud. But before I do that, like if you compare to software, I completely agree it's the foundation. Yeah. But unlike software, where a small team of 4 people can iterate and come up with something fast, it's very capital intensive. If some startup or some innovative company want to disrupt, all of you represent large organizations, with very established posture. But if some startup want to, do you think there's still a space for being funded and in the semiconductor space and disrupt this, take advantage of AI, while we have hundreds of AI software layer companies popping up every second, right? So
as a startup guy myself, 100% yes, right? The opportunity in terms of one of the VC panels who were saying, VCs are in the business of disruption, right? And if you look at the incumbents that are delivering to AI solutions, right, those incumbents are looking to be disrupted, right? When you're delivering a solution that is tens of billions of transistors, right, and the compute is a small element of the performance needed to deliver training or inference, right? But yet, the compute is where the energy is going from an innovation standpoint. There's an abundance of opportunity for startups to innovate, right? And one of the same panels said there's $1.6 trillion sitting on the sidelines waiting to be invested, right? They're looking for ideas, right? I think this is a target-rich environment. So yes, startups will get funded.
Maybe I'll just dig into the point that he's making, Anand. Right, the key point is that, yes, a lot of work has been done. The topologies are well understood, right? You have these vectors and matrix engines, everybody has them. But there is huge opportunity to innovate on the silicon side as well, right? If you can come up with something, some of the angles that people have looked at, which is, what people are realizing is that you have to spend a lot more energy to move the data for AI. If it's a 100 billion parameter model, if you're moving the 100 billion parameters, you're expending an amazing amount of data in amazing amount of power in moving the data. LLMs are really memory bound. They're not compute bound. It's not that you're going to put in more TOPS and you're going to get better performance. No, it's really about the memory bound portion, right? So for example, if somebody can really crack the idea of in-memory compute, or if somebody can crack the idea of near-memory compute, these are all areas that are ripe for being able to take something that's in the range of, let's say, 10 TOPS per watt to the range of hundreds of TOPS per watt, right? Those are the kinds of innovations that are still there to be had, I think.
And as not the startup, but the re-startup guy, given MEPS's history, what I'll say is, see, we've also got to break a few myths about semiconductors. And I moved from TI to MEPS, and very different environment, et cetera, right? And what I've realized is that I don't think any one startup's job is to go change the entire chain. I think it's the focus of saying, let's go pick 1 or 2 problems. Near memory compute, here we should talk, maybe an interesting one. But then also use AI to be more efficient at it. The number of designers it takes us to come out with an SoC of a reasonable amount of complexity is only going to reduce if we start using AI to go create solutions for AI. And I think there is a lot of opportunity there, both from an EDA side, but also how we do design methodology and what we want to do. Combine that with whatever we're trying to go do on the chiplet side. I think there is help coming. And I think this is a startup-rich environment. The only data point I'll point to the contrary is 90% of the AI investment today is directed at software on AI, which is 13% of the AI revenue. 87% of the AI revenue, thanks to our friends at NVIDIA, is on the hardware side, and also Marvell, sorry, and Qualcomm. But fundamentally, 87% of the revenue is here. I think that's the, if I may say in a very humble way, the education we need to do to the VC community that there is revenue to be made on the hardware side and innovation, but it doesn't need to be billions of dollars of investment.
So I think your point of view will be important, given you started a chip
startup.
startup.
So I'll add in. So I think if you had asked this question 10 years ago, people would have said, yeah, okay, it's a dead industry, nothing interesting happening and so on. But right now, it's considered, for the last few years, actually last 5 years, it's considered renaissance of semiconductor. And the reason is that now these applications are driving, as Anand said, the needs, which is actually making you think, okay, I have to do things differently. As we all know, the performance of the AI models are really limited by the memory bandwidth of HBM, which HBM is a high bandwidth memory, very close to the processor. There are a lot of innovations are happening in how do you get data faster and more amount of data. How do you move data around between the AI processor much more efficiently and so on? And each one of them to me is a semiconductor is a great area where there is a point of inflection. There are many point of inflection here in the connectivity area, in the packages area, because these are very complex packages. Also, they are very expensive. I mean, a typical AI processor is like a $10,000 cost. It's just ridiculous, right? So there are many innovations going on, and those are all opportunity. In fact, in the last few years, a lot of startups have been not only funded, but as a proof point, one of the connectivity startup, which actually does nothing but PCI retimer. I mean, which would have been a joke if it was 20 years ago. I mean, they won't get any valuation. They had like what, $12 billion. They just went public a few months ago. Astera, they have $12 billion valuation. The revenue is like $300 million or something. So look at the multiple that they got, just because they will bring, they have a promise of bringing something, solving a problem in the AI cluster, right? So every time you save a watt in a AI solution, it's actually you're saving a megawatt. That's the way they see it, right? So imagine this chips that I'm talking about is 700, 800, 900 watt. Imagine you save 100 watt. You are saving 100 megawatt in a data center actually. It's a huge deal, right? So saving power, the impact is huge. And then the cost impact is also huge, because if you just save, let's say $100, is like you're saving $100 million, because of a large data center cluster has a million devices. So the percentage improvement, because the cost is so high and power is so high, even a small 1 or 2% improvement has a order of magnitude impact. And that is why a lot of funding actually is going on right now, and a lot of innovations are happening.
Can I add a comment to that? You asked the comment about, is the environment good for startups in semiconductors, given the AI thing, right? I answered it, but I'll add something to that, right? Startups benefit when there's chaos. Startups benefit when there's a lot of Brownian motion, right? Large companies, Intel, Qualcomm, NVIDIA, are fantastic at applying heat to an environment that's got a lot of Brownian motion, turn it into convection current, right? Drive some stability. But when there's Brownian motion, startups excel, right? They can wiggle in and out of opportunities way faster. And he just gave a couple of fantastic examples where those examples, I will argue, are much more difficult to give birth to inside of a large company, right? So it's a fantastic environment actually for startups in silicon. No question it's more expensive to do a silicon startup than a software startup. Just the cost of doing a mask is going to be quite significant. But the environment is right.
Wonderful. So basically, you think VCs will be investing. I mean, there's an environment.
They are.
Okay.
They are,
okay.
actually.
So let me come to the architecture next, right? So the most famous company right now, I mean, is NVIDIA in terms of, but if you look at AI, it's training, it's inference, it's edge, it's heterogeneous architecture. So just break it down for me. So do you think this dual stage or heterogeneous architecture with a lot of edge intelligence, AI, is the way to go to scale? And I think I know, Ziad, you're very passionate about it, so I'll start with you first.
Sure, thank you. I think, there are many engines that we all have in our products, right, that can do AI processing. You have a CPU, typically it can do processing. NVIDIA has a GPU, so they use GPU for processing. But I think if you look at doing custom architectures that can actually do AI, you'll probably be able to get to much better power consumption per, performance per watt. And that's what there is the innovation aspect over there too. So that's one set of heterogeneity that you can work with. There is another hybrid approach that we talk about, which is it doesn't have to be just edge or doesn't have to be just cloud. It can actually be a combination of that depending on exactly the environment or the use case that the consumer is seeing, right? If it's a use case where you're running, 100 billion parameter model, you're not going to do it on the edge. You will do it on the cloud, and it's perfectly fine. But I think there are certain trends that we see. So for example, number one, if you guys look at ChatGPT 3, it was 175 billion parameters, right? ChatGPT 4 is like 1.7 trillion parameters. But if you look at Llama, that Meta basically launched, we're working with Meta on that, it's also a chat bot-like model, and it's 7 billion parameters. Llama 3 is 8 billion parameter model with a context length of 12K. It's pretty large, right? But what you also see is if you look at the characteristics of these models, they actually compete fairly well with ChatGPT. So what's happening in the industry is when a new modality comes, it's a large model. Over time, algorithms get better, data gets curated. You actually get to a point where the model becomes significantly smaller. That is what is opening up the avenues for a lot of that transition to happen from the cloud to the edge. I mean, you talked about 800, 900 watts of power on some of these GPUs. We run in milliwatts, right? Our thought process is much more milliwatts because we still got to run on a device that's going to last the whole day. As you do that, you're actually bringing in a lot of those benefits. I think somebody said recently, if you took all the capability that you needed today for generative AI, you would not have enough power in the world. We were working with a company, or rather with a professor in UC Riverside, and he's showing data that to run a single LLM session, you actually burn a bottle worth of water to cool down. There is a sustainability problem also with generative AI if you scale it with all the use cases, all the users, and just the size of the model. So really, the way I usually put it is, you need edge to get the full capability out of the generative AI revolution, in addition to the cloud.
Anybody else want to add?
I can go. Given I'm the CPU guy with MEPS, but look, I think we will make progress in terms of the architectures when AI processing becomes processing. So if you play this out, in my opinion, 10 years from now, I think there will only be one kind of processing, which is AI workloads, because everything is going to translate into an AI workload to some extent. So the answer is going to be, like Ziad said, right? It's going to be a combination of edge and cloud. It's going to be a combination of various heterogeneous elements. Today's AI processing is very hard cuts. Here's a GPU, here's a CPU. These PUs are going to exist. But fundamentally, we've got to start distributing AI processing in how we think of processing architectures. It doesn't have to be big iron AI all the time. It can be distributed. It can be bump on a wire kind of inference, which I think will propagate more on the, bring it to the edge. And I think that's where the architecture, I think it has to be closer to how nature takes care of things, which is more steady and natural versus just jarring cuts of things. And I think that's the evolution.
So I wouldn't say that's the evolution. So as you know, Faisal, my entire career has been about accelerated computing. I started in 2000, accelerated. My view is this, as the data is growing, to get the efficiency, to get the best power, you have to have application-specific custom solution. That's what we have been doing for the last 25 years, and that's what we are doing right now, because even every hyperscaler wants to save power, wants to save money. So it's a accelerated computing custom silicon that we work when we work with them to enable them. And I completely agree with that. It doesn't stop there. As you go to various aspects of the distributed data network, you need to have optimized solution for every node. And that's actually is where I'm saying is gonna drive even more need of silicon, because you need to optimize for every dollar and every watt. So yeah, I think the future is of accelerated computing, and that's what we are focused on.
So I think you all touched upon the point. The elephant in the room, I think, is power and the cost of running it, right? So you gave different options, distributing to the edge. Do you think it will require, right now we're not talking about it, and the model's getting smaller, optimized as much as we can, but do you think that's a sustainable part to achieve the power? Because if you run all the training and all the things that we want, we don't have enough power in the grid right now. So is it some revolutionary redesign of the architecture will happen specific to LLMs or the way we read memory, or that will significantly alter it, or these will be the incremental steps that we are doing, and we'll get to a point that power is not an elephant in the room.
Can I start? So it's already happening. By the way, then the data center of today is not the data center of 5 years ago used to be, right? So people are recognizing that problem, and they have already started optimizing and kind of redesigning the entire network, redesigning the interfaces. There's so many new standards that have come up. Coming up with a new standard of accessing data from the memory. All those things are happening actually already. And I think this is where the biggest startup, like a greenfield is, that this is an area where every incremental value add will be welcomed, adopted very fast. So this is, I encourage everybody, it's a physical, it's like a science problem. It's not really just a math problem. And every aspect of that needs to be optimized.
I agree. I think it's happening. I mean, we're spending a lot of effort today trying to do accelerated computing, trying to go figure out how we attack that power problem. It's happening. Now, it's not going to be one big chunk. I think there are steps to it, but it's happening.
I mean, I would focus on saying that absolutely the right points, but I think this innovation is needed at every level. I'll go back to that. Models need to get better. For example, I mean, I've spent a lot of time, and I used to talk to some of the industry leaders, and they'd say, "Why do you guys talk so much about quantizing the model?" Well, now you look at a model that's 7 billion parameter, and people are like, "Oh, if you quantize it, it takes much lesser memory in DRAM," right? So even to make the model fit, to be able to process it. So we learned a lot of these techniques to prune the model, to compress the model, to be able to quantize. Some of these techniques that we use on the edge, they don't have to be just in the edge, right? It can be used anywhere. But at the same time, what it allows you to do is to change the model in a way that you still can maintain as much of the accuracy, but get a lot more benefit in terms of power. If you're processing 16 bits, because the model gets trained, comes out in 16-bit float, you actually run it in the integer domain in 4 bits, you can imagine how much power you've just saved by doing that, right? Those are some of the techniques at the model porting level. Then there are techniques at the hardware level. There is techniques at the compiler level, right? People use sparsity and other techniques to be able to. So my point is, at the full stack, you have to look at opportunities across the board to be able to get to a point where you can actually run these models at much lower power consumption. We do that in a smartphone, like I said today. You can run a 7 billion parameter model. You can do text-to-image like models like Stable Diffusion. At power consumption, that's actually not going to change the battery life of the device for a normal use case like scenario. So you can imagine if this scales, if a bulk of the workload that people are doing for productivity applications, or for the stuff that you're doing on your device, for kids or for social networks or what have you, all of that will add up to, I think, huge savings if you do use these techniques.
Okay, very good. So there is compute, there is interconnect, there's memory. If you step back, all of these have to come together to give you the most, their optimization all across, right? Like SoC, or you can say that everything has to fit this new model. So how are you approaching it? Are you approaching it that you're optimizing each of them, like the way interconnect happened, the way memory, you were talking about different memory options that are there to optimize all these solutions. So each of your respective companies, like how are you approaching that? Like holistically, or you're saying that point that like we need GPUs and NPUs and but then there are other elements also, right, to get the full solution.
So we are approaching at a network level, not even at the system level, and we work closely with our top customers who are all the large data center guys, and we are participating in architecting as well as pushing the envelope of innovation in each aspect of that, all the way down to the silicon itself. So yeah, we are involved in every aspect.
Yeah, I think what we're trying to do different is CPUs have catered to the hardware engineer for a very long time. We are trying to cater to the software engineers who understand these workloads. And we're trying to tune, and Raghu used the word application specific, we're trying to tune our CPUs closer to the workload. Now, the problem is people who design CPUs take different classes in schools versus people who design workloads. So honestly, bridging that gap is the most interesting problem from a human capital perspective. But if we are able to bridge that, we'll start talking the language of a software engineer, implementing it closer to a CPU, and I think that gives you a better solution.
Right. Maybe I think Anand, vendor agnostic perspective, right? So I think more holistic. I think what will you chime in?
I think you're seeing a lot of innovation happen, and one of the remarkable things that I find about semiconductor industry at large and the tech industry is we're extraordinarily pragmatic, right? When you have to put a whole bunch of investment into the ground 5 years before the demand is actually present, it forces a level of pragmatism and realism that I don't see in too many other industries other than maybe oil and gas, right? Where you have to drill for oil and so on. So I don't think the solution here is going to be a magical silver bullet. I think it's going to be incremental. There'll be a bunch of different things that get tried. When you coagulate across all of them, you're going to see a breakthrough, right? And you're starting to see that happen already, right? I do resonate a lot with what Samir said, right? The applications have to get catered to, and the applications, the workloads are changing very, very fast, much faster than I've seen ever in my 30-plus year career, right? And so if there's one breakthrough that I think can play huge dividends, right? It's how can we get the underlying silicon architecture, I don't care whether it's CPU, GPU, whatever, right? The mating of the evolution of that architecture to the evolution of the workloads, right? There's currently an impedance mismatch. If you get that impedance mismatch to be a bit closer, I think you're going to see giant breakthroughs. And maybe AI and LLMs can help in that arena as well, right? I have a sneaking suspicion that it can, right? And
so with AI, there were questions about regulatory aspects, security, compliance, and I think my question would be, is it mostly software infrastructure companies that are playing a part, defining that and assisting in that, or semiconductor companies also have a role because you are the foundation as the policies are defined and regulations, and we have those controls or things built in that can implement those guidelines. So do you think semiconductor have a role in there, or is mostly software layer that that will work?
I think semiconductor companies absolutely have a role, right? I think all companies that have a presence in moving the current state of AI to the next state of AI, which clearly includes semiconductor companies, have a role to play in what the regulatory environment should look like, right? I'm not a huge fan of a huge amount of regulations. Yeah. I think it stifles innovation, right? I am a fan of some light regulation, right? And I'm not a policy guy, I'm not a politician, so I don't know what the answer there is, right? But is there a need for some regulation on AI? Yes, I think there is, right? And there's probably smarter minds than mine at work trying to figure out what that is.
I'll comment, right? I mean, absolutely, right? So we actually have done things on these lines, right? So one of the things which jives extremely well with the whole on-device idea is this privacy aspect that also comes with this, right? If you're, let's say, you have a PDF document, and there is a LLM that you're running, and you want to actually summarize it. Well, now guess what? The document is sitting on a server somewhere else. It's no longer private, right? If it's a confidential information, if you can do it on the device, it preserves it the big way. Another step that we have taken is we are partnering with a company called TruePic at Qualcomm. What it does right now is, for example, you take a picture. We have the election season coming up. There's a lot of generative AI that can actually create a lot of fake news, as we call it. But what this allows you to do is actually go into the metadata of that image to make sure that the pixels that you captured as you are actually storing that image, they have not been tampered with. Now, to be able to preserve that, you need to go all the way to the bottom of the silicon. We have something in our part that we call hardware root of trust. You need to have that hardware root of trust to ensure that when the OS is running, no other application is coming in and tampering with that data. And actually what it does, it puts a seal that says this data or this image has not changed. If you change it, it puts that in the metadata that now the image has changed, right? You need techniques like that. We're working with NIST. We're also working with a consortium of companies called ML Commons. What ML Commons is doing is actually creating a benchmark of saying, hey, here are all the different LLMs, models that are coming, and there's a new one coming on a daily basis, and they're actually putting a criteria to establish safety that comes from the model. So, there is a safety aspect at the model level, there is guardrails that you can place, you can do a lot of technology, a bunch of people are working on it, you can do it at the hardware level, you can do it in the OS level. We need to do kind of at all those different levels again to do it right, and that's why semi definitely comes into play.
Well, one quick question, right? So if you look at the journey, like whether you look at compute, we started with mainframes and where we end up, the feeling is that AI, we are in like day 2 of it, like, next 15, 20 years, what's going to happen, right? I think it's accelerated a lot. The innovation has really, it's a mind-blowing that how fast things are happening. But it's very hard to predict how it will be 10, 5, 10, 15, 20 years. So how are you guys making those decisions? Because you are hardware, they are longer. Your decisions are a lot more permanent than compiling and changing a new binary in a day or so. So how are you making those decisions to make sure that you can forecast how it will be and make the right decisions?
So this is a very interesting question, and that is the toughest problem. So of course, what kind of various compute will come, nobody knows right now. However, what we know is based on the existing models and based on the existing workloads and so on, that the fundamental things needs to be done. Like, for example, you need more bandwidth, you need a ability to share data and so on, you need to reduce power and so on. So a lot of investments are going in that direction, keeping in mind that in a multi-chiplet environment, that maybe the core of the logic may be replaced 3 years from now. But having this whole framework developed and tested and ready for production, that by itself is a lot of work. So that's what is going on in parallel. As you correctly said, the cycle has improved a lot. I mean, if you go back like 20, 30 years back, a typical new processor used to come 5 years, once in a 5-year cycle, right? And Intel then came up with a brilliant technology, the TikTok, where every 3 years a new one will come. These days, every year a new one is coming, right? So yes, AI has helped to accelerate this whole process as well, and it's a constant kind of aligning yourself what's going on. Something changed, something just fundamental remains the same.
Anybody else?
Yeah, I'll add right to, I mean, something Samir said earlier, right? If let's say you hear about a company today, hey, I'm going to do silicon that's going to do an ASIC for just doing LLMs, you probably should not invest in them, right? Because what's going to happen is that model is going to change tomorrow. And if you do not have that flexibility in your solutions, you will not survive. So when we are defining the products, I mean, I just locked in some products that we're going to actually commercialize in 26 and 27. You better have that flexibility to be able to adapt to these very different models. Today, it's autoregressive models, right? Each of that word that LLM produces, the whole 7 billion parameter model has to run through it every time. You think this approach will continue? Probably not, right? You will get to state space models. You'll get to, there are new models coming like striped hyena and all these other models. You need a very flexible topology on your hardware side to be able to make sure you're not locking yourself out of any of these combinations. LLMs, like I said, they are memory bound. If you go to LVMs, which are more like the large vision models, they are actually compute and memory bound. So if let's say you went and solved the memory problem, but you did not solve the compute problem, you're still screwed. So I think that's the whole idea. You need to make sure that you are, with the pace at which this thing is changing, you need to have the flexibility to adapt.
I'll just leave it with one thought. With LLMs, we're effectively trying to mimic our brain, right? Our brain runs on a few watts. These machines that are required to run LLMs run a few hundreds of watts, right? Ultimately, it's innovation that's going to get that down to maybe not a few watts, but close, right? So I think there's a tremendous amount of opportunity ahead. I'll rest on that.
In the interest of time, I would like to thank all of you. I think a big round of applause for all 4 leaders. And thank you. And interesting data point, out of these 4, 2 are my class fellows. So, you can guess which 2 are. Okay, thank you.
Thank you.